materials have always been a bearer of new technologies and subsequent societal development and advances. The most simple examples, we go back in history and think about the Stone Age, which developed into the Bronze Age, and then it went on into the Iron Age. And each age is labeled by the material that was bearing the new technology or the new society as a whole. And every new material was better than its predecessor, and it also made life simpler for the people of that age. I think in the beginning it made life bearable just to exist. And this is the way it has gone on in our society, and still today we always have new technologies that come with the introduction of new materials or substances. There's a new development that has come only in the latest decades or so, and that is the ability of using basic sciences like physics, chemistry, combined to material science, and we are able now to, atom by atom, design new materials with designer functionalities. And today, I'll talk about the ultimate material, which is actually not designed, but it has been there all the time. And you see a picture of it, and you have been playing with it since you started to use a pen and doing the calligraphy that we just heard about. So it's all about one layer of atoms, and it's known as graphene. And this is what I'll try to spend a couple of minutes of your time to explain. Graphene is amazing. It's the material of superlatives. It's best in everything. This is what we are told. Of course, this is a truth with modification, and it's a truth that has to be verified. But still today, when we think about it, it's only one atom thick, or thin, how you want to put it. And this is a material which theorists like I have said, this is impossible. Any thermodynamical fluctuations will correlate up, and you know when you are in a hurry and you take your glad pack and want to cover something and it all curls up. This is how it should behave. But then these guys in Manchester, under Gaiman, Kostya, Novoselov, said, okay, this is impossible, let's prove them wrong. And just shy of 10 years ago, they published results showing that you could actually make useful things and address this single layer of atoms. This material is the strongest material we know. It's stronger than diamond. Diamond isn't stable. It will fall into graphene if you just excite it with a little bit of energy over a threshold. So graphene, or graphite, is actually the stable form of carbon. And being the strongest, it's still flexible. And now being the strongest, one wonders what would you do? But if I had a hammock of graphene here, then I could put the baby and it would rest in thin air in your eyes. It's not that I could put a truck, but a 4-kilo newborn child. It's another issue, another property which is nice, and that is that it has a width, a length, but it has no height, so it's only surface. So you can address it all over. So you have this big sheet which you can work with. And then it's strange in that sense that I can put any material, substance on top of it, and it won't let it through. It's impermeable to other elements and substances. And being so thin, if you take the amount corresponding to a bite of a Snickers bar, that's 10 grams roughly, you would cover 3 football fields of graphene. We made a calculation. I'll talk about it going into electronics. If you take 15 kilograms, you cover all the displays, computer displays, iPads, whatever, with graphene. It's something that I could carry along. That's the world production. It has other properties. It's the best thermal conductor. It carries heat extremely well. It's one of the best electrical conductors. It carries charge extremely well. And on top of this, it's transparent, so it lets light through. And what one has seen is with all these superlative properties, you can probably make quite a lot of interesting things out of it. And this is what I'm going to try to dwell on a little, giving you some examples, and also showing a little bit what me and my colleagues are doing up at Chalmers nowadays. But first, I thought I'll give you a crash course in science. And if you take the picture here to my left, you see a chicken wire with black spots in the apexes where the lines meet. That's the carbon atoms. And they organize like this by themselves. And the reason why they do that is carbon has the possibility of making a lot of different compounds. And it has 4 electrons in its outer shell, which are responsible of it. It's very easy. It's with these nice blobs that I have shown here. What happens is 3 of them will fall in a plane, make something a chemist would tell you is sp2 hybridization. And the neighboring carbon atoms want to share electrons with each other. And they do this very well. It's a covalent bond, it's called. And this bond is extremely strong. This will make graphene the strongest and also flexible material that you have. So mechanical properties comes from this simple electron bonding. And then we have the blue guy, which is the electron which is left. And due to quantum mechanics, it doesn't know if it's on top or bottom, because you have some uncertainty, as you should. But this electron skates around this chicken wire with the speed of light in that material. So it's basically a relativistic particle. It has no mass, so it was a big excitement, of course, that now we can do really test fundamental physics in this material. And this blue guy is responsible of the heat carrying, the electrical charge, and also the transparent. And now, of course, you can start playing around, combining properties or exploring special properties as far as you can. And this is something that we know of as translational nanotechnology. And I show you 4 examples, and I'll go into 3, perhaps a little bit more in depth. The first one you see up in the left corner is the possibility of making flexible, transparent electronics. And this is a bit of science fiction. I would take up a roll of plastic. It would look like it's transparent, and I'll get today's news of whatever I'm subscribing. I get a movie, I get whatever. So you can have a piece of material which is flexible and still communicating. So it's just a new way of communication and information processing. So ICT, that's information, communication, and technology, basically. That's short for that. We have another one, which is down in the corner, and you see an airplane there. And as graphene is so strong, you can put it into composites. And it's not only strong, it's extremely light. And this is quite important, because now you can make big chunks of this material and put it into, let's say, the body of an airplane. You cut the weight by a lot, and the fuel cost will go down, and you can just do other kinds of vehicles, basically. Up in the right corner, you see a face of a small car which is plugged in, and we all know about that we want to have electrical cars to cut all the emissions and so on. And graphene is essential in that, because it has promise of making very effective batteries and supercapacitors. That's batteries that load very quickly. There is an idea of having supercapacitors to drive Älvsnabben, you know, the little boat going across here. Basically, every time it docks, fueling up with electricity and shooting back and fueling up again. Nowadays, you know that if I want to take my iPhone or my car, I need to spend hours to get it loaded. Now you could do it in a few minutes. And then one thing which is very interesting, you see the picture here, you see a DNA strand, and it's going through a hole which is made in graphene. And the idea here is that pulling it slowly through the graphene mesh, you could sequence the DNA and understand more. There were 4 scientific articles that came out the same week with the same kind of picture. So what has happened with this is basically imagination is the limit, but we still need to prove these things. Now I want to say a little bit in depth about graphene. And here's something that came earlier this year from a group in Germany. And they were playing around with graphene transistors in a liquid, and they realized that they could operate them and make them interact. And of course, there's a big problem. Let's say your eye is destroyed for some reason, but your visual cord is still working. then you would like to connect that to something biocompatible and give it impulses, because one knows that you can regain sight in a sense. And today you do this retinal transplants. But in this idea, graphene seems to be biocompatible, which means that if you let graphene interact with a nerve cell, it will meander out, and it's ready to take the electrical impulses that you can feed it. And this you would do by placing a camera, just like this CCT camera, which would give the impulses to the graphene membrane, and then it would trigger impulses for this. Another important thing in today's society, it's interesting, it's important, but it's extremely problematic. That's our need of having vehicles to get around. And this is a concept car. There have been many different concept cars always around to solve different problems. But this one is now very integrated, and its idea taken out by Daimler in this case, but there are others. And it's this smart car. Already today, if you go to Berlin, you see them like we have our bikes in Göteborg. They have their cars that you can subscribe to and drive around. Very interesting. But this car now, you have integrated. You have made the chassis of a composite material. You have made the roof smart materials. So it's like a solar cell. So it's picking up energy from the sun, which it feeds back to its graphene-based battery, which is driving it. So it's fueling as it's going. And of course, you can always top off quickly at some station. And it also could have smart material in it, because you could have transparent electronics, so your windscreen would be your display board and so on. So there are a lot of these ideas which are working on going in this direction. I have a third example, which I think is extremely important, because this is perhaps one of the big sources of war today. Water supply. We have a lot of water, but 98% of it is too salty to use. So people have thought, okay, let's desalinate it, take away the salt. Turns out that this is an extremely energy inefficient and hard process to do, and it's slow. Now, this is based on a computer simulation where you have a divider of graphene, where you have made nanoholes in it, and you have decorated the holes by hydroxy molecules, and you apply a pressure gradient, so it's reversed osmosis. And what you have to the right is salt water, and this little hole is selective. It lets only the water through and leaves the salt on the other side. And it does it to 100 to 1,000 times more efficient than any other process, available process in this kind of in this field. What I have told you about now is great possibilities, and of course they are still. This is a computer simulation. There's no experiment yet, and the car doesn't exist, and there was only an idea. But the potential of this material has allowed the European scientists to go together and actually get the big funding from EU on the level of €1 billion euros over 10 years. And how it was sold to them is this funny picture. I hope you don't start reading now, but the idea, let's focus on the color scale here. To the left, you have the idea of science. You have this fantastic material of superlatives. You have the bright ideas of designers, engineers, and etc. You have other materials. Once you have proven that one is possible to do two-dimensional, you can have more. And the idea, what is said, that we want to take this, and we want to be able to compete to Asia and Americas and so on, and go together, because you have to make this a joint effort. And the idea is that we want to take this material over 10 years from the blue to the red, and that means going from academia into industry. And of course, you can sell it on making faster computers, ICT, and so on, and you can have energy and all these important things. But the most important thing, when you pick the mind of the guys in the EU, is that we bring people together, we make societal changes, giving job opportunities, education, and actually working together. This was what they were interested in. I asked them, what should I tell you in 5 years? And they say, well, It wasn't so important that all the big gains in technology, of course they're important, but it was this, that we could work together, because we are 17 countries there, of close to 200 groups working together. Okay, that was a little bit about visions and so on. Let's talk a little bit more about how it's produced. There are several ways of producing graphene. The first one you heard about is you take some tape, you take some well-defined graphite, and you start ripping it apart, like this. Take 6 rips, and you have graphene. Even the king can do it. Anyone can do it, under guidance. It's extremely easy. But you need a microscope, you need to have the ideas, and of course. And then you have to find it. That's very hard, because you get a square micrometer of this, so you have to find it. So, of course, we want to make high-speed electronics, so you have do this, you have silicon carbide, and you evaporate the first layer of silicon, and you get very nice, compatible with electronics industry. And in fact, in Linköping, within our projects, we have the first graphene producing company in Sweden. You have down in the right corner, you put graphite in liquid, and you shake it with ultrasound, and it falls apart. And this you can print, and you make printed electronics, which is superseding any printed electronics today. The thing that my colleagues do at Chalmers is known as chemical vapor deposition. That means that you put a hot copper plate or some metal in a furnace, and you introduce carbonous gases. And those dissociate, and the carbon falls down on the metal, and by self-termination, it makes a single layer of graphene. And the guys we are sort of competing with in Asia already made 100 meters, 20 centimeters apart. And of course, this is now possible for all kinds of applications. What they do in our clean room is they make the graphene by the CVD. They use a process which is close to a battery process to bubble off the graphene. And then you see a picture of a typical size of graphene. It's limited in our place by the size of our furnace. But in principle, I used to say that all these fantastic things we're going to do with this size of my thumb. So we need to scale up a little bit, as you understand. But the idea is this. We can make the graphene, and we can now go on and into our research. This is also too busy. Please don't try to understand everything of this picture. But the essence of this picture is that we have groups that are making vertically emitting lasers for communication purposes. You have fiber to your homes, some who don't live too far away from urbanization, but you know, you use light for communication, and then they're making these lasers. And one of the basic properties is this, that they need to have. They need to have a transparent, current-spreading electrode in this. And there is where we try to see the properties of the graphene that was made. And they feed it back, and they feed back to the process, and we learn all the way how to do it. But this has even more consequences, because transparent electronics today is done with one of the scarce materials, indium, in indium-10 oxide. So, I mean, I guess we had some polls in the previous talk, but everyone raised their smartphone. We all have it. And there's an enormous demand, because everyone in the world wants to have it. And it's really one of the most scarce materials that you have. So the promise of this basic research is to work towards trying to replace something that everyone wants to have. And we all know the iPad is great, but it's not flexible, because graphene would be possible to make more alternative functionalities and shape and form of this. And if you compare indium-10, indium is among the 14 rarest elements, and carbon is the 4th most abundant, so we have a lot of possibilities here. Okay, so coming back to where I started, I hope you got some kind of flavor that in this simple pencil drawing, where you actually have produced not graphene, but probably quite thin layers of graphite, actually could hold a promise for the future.